All right, so in this video here, we will be defining a new number system called the complex numbers. Right, so to define a complex number, what we're going to do is we're going to specify a pair of real numbers, x and y, and the complex number is going to be denoted by x plus I, y, where I is a fixed symbol. Right, so given a pair of real numbers x comma y, the complex number is going to be denoted by x plus iy, where I is a fixed symbol. And now if we take all possible pairs of x and y and write them in this form here, x plus iy, this all possible set is going to be denoted by the set of complex numbers, and we're going to denote it by this bold C here. All right, so again, a complex number is going to be specified by x plus iy, where x and y are a pair of real numbers. And if we look at all possible complex numbers, we're going to denote this by boldface C. Right, so that's our new number system, which we're calling complex numbers. Right, so if we want to define this new system here, what we would like to do is we would like to be able to do some arithmetic on it. If we want to do arithmetic, the starting point is to define what it means for two numbers to be equal, right? So that's the first thing we would like to define. So in the case of complex numbers, we say two complex numbers x plus iy and u plus iv are equal if and only if x is going to equal u and y is going to equal v. All right? So if the x here is equal to u and the y here is equal to v, if both of them are equal, we say that the two complex numbers are equal. All right, so again, it's important to kind of keep in mind that complex numbers are going to be specified by a pair of real numbers, x comma y. All right, so now that we know what it means, what are complex numbers and what it means for them to be equal, the next thing we'd like to kind of talk about will be how do we go about representing them. All right, and we're going to begin with Cartesian, and then we're going to move on to polar representation. All right, so let's say we are starting with a complex number, which we're going to denote by z plus z, which is equal to x plus iy. Right, so and as we mentioned last time here, x and y are real numbers. So they're just a pair of real numbers. All right, so now remember the order of these numbers are going to matter. For instance, x plus iy is going to be different than y plus ix. So as soon as we specify a complex number, what we're doing is we're specifying an ordered pair of real numbers. And so if we have an ordered pair of real numbers, x comma iy, we know how to plot those on a Cartesian plane system, right? So if I give you a pair of real numbers, x comma y, the coordinate, if we want to plot that on a Cartesian plane, what we would do is we would go x units in the x direction, y units in the y direction, and this point here is going to be exactly x comma y. Right, so this is how we're going to represent complex numbers. We're going to represent it by plotting the pair x comma y. So a few notation here. If we're given a complex number z is equal to x plus iy, then we're going to denote x as the real part of z. And y we're going to call the imaginary part of z. Right, so x here is going to be the real part of z, and y is going to be the imaginary part of z. And therefore, sometimes we're going to denote this axis as the real axis, and this one here as the imaginary axis. All right, so next, if we know that a complex number can be represented as a point in the Cartesian plane, using xy, we know there's another way of representing points in a Cartesian plane, right? And that's what are called polar coordinates. So if you remember what polar coordinates are, we specify r theta, right? Where r is going to be the distance from the origin to that point in question, and theta is the angle this line here makes with the polar axis, and in this case that's the real axis. And the relation between x, y, and r theta is given by these following two equations. We know x is r cosine theta, and y is going to equal r sine theta. All right. So then in our case, z is going to be x, which is r cosine theta, plus I times y, which is r sine theta. And what we're going to do is we're going to factor out the r and write it as cosine theta plus I sine theta. And this quantity here, which is cosine theta plus I sine theta, we will write it as e to the I theta. Right? So for right now, we'll treat it as a notation, but the justification for this will come when we actually define the exponential function for complex numbers. But for right now, we're just going to say, hey, cosine theta plus I sine theta, we're going to denote it by e to the I theta. So then this here becomes r e to the I theta. So z is x plus iy, which is r e to the I theta. Right, so this r e to the I theta is called the polar representation. X plus iy is going to be the Cartesian representation. Right, so both of them are going to have their advantages and disadvantages, as we're going to see as we proceed along, but it's very helpful to have both of these representation in mind as we work with complex numbers. All right, so a few properties of complex numbers. So first, we're going to talk about the modulus or magnitude of a complex number. So if we have a complex number z is equal to x plus iy, the modulus of a complex number, which we're going to denote by absolute value of z, and that's going to equal square root of x squared plus y squared. Right, so that's the modulus of z. And z is going, the modulus is always going to be positive. All right, so for a second here, if we think about the modulus here, which is square root of x squared plus y squared, is that related to the polar coordinate system in any way? So does this quantity here, radical x squared plus y squared, represent anything in our polar representation? If you think about it for a second, you should come to the conclusion that this modulus here is exactly the r. It's the radius, right? So that's what we're computing here, is the distance from the origin to our complex number x plus iy. So the modulus here, which is the magnitude, the square root of x squared plus y squared, is exactly r. All right. So with that in our mind, what we're going to do is we're going to look at the following example. And the example, what we want to do is we want to express square root of 2 square root of 3 minus 2i in this form r e to the I theta. So what I'd like to do is, if that's our x plus iy, I'd like to find r, and I'd like to find e to the I theta. All right, so first, remember r e to the I theta is just r, and this is cosine theta plus I sine theta. And if we rewrite this, this becomes, so let's leave it here. So the first thing we know already is we know how to find r. Right? So our x here is 2 radical 3, and our y here is negative 2. So if we use that, I get r is equal to square root of x squared plus y squared, and if I plug that in, I get 2 radical 3 squared, which is 12, plus negative 2 squared, which is 4. So that comes out to be square root of 16. All right, so that's our r. So if we think about it, we know cosine theta is equal to x over r, and sine theta is equal to y over r. Right? So what is our x here? Our x is 2 radical 3. So our cosine theta is 2 radical 3 over 4. And our sine theta is y, which is negative 2 over 4. And if we simplify this thing here, I get radical 3 over 2. And if I simplify this here, I get negative 1/2. All right. So now what we're going to do is we are going to find the theta in this here. So theta is going to be between 0 and 2 pi for us right now. So what we're looking for is we're looking for angle theta such that cosine of theta is radical 3 over 2 and sine theta is negative 1/2. Remember, cosine is x. So we're looking for angles where x is radical 3 over 2 and y is negative 1/2. And we're going to identify that right here. It's 11 pi over 6. So theta is going to be 11 pi over 6. So what that means is our complex number, which is 2 radical 3 minus 2y, can be written or represented as, I want to make up my mind, 4e to the 11 pi over 6. Right, so that's how we would go from Cartesian representation to polar representation. The other direction is slightly less challenging than this direction here, and I'll let you do that on your own for homework.